Starting with the name of Allah Almighty, this is Rajab Ali. Today I'm going to represent my final year project of inductive wireless power transmission based non-destructive testing for detecting surface defects. We are working under the supervision of Dr. Junaid Ahmad Bhatti and co-supervision of Engineer Umar Abdul Majid. This is the outline of our presentation. We will introduce our project, motivation of our project, problem statement, literature review, aims and objective, methodology, results, conclusion, future recommendations, and references. Introduction. Maintenance of equipment and material is necessary part of industry. Its evaluation is important part of structure and their design. The world's industrial companies and corporate sector which utilize variety of material structures and machines and for their safety. It is important to recognize and measure their fractures and failure points. So researchers have produced two testing methods, destructive and non-destructive testing techniques, which helps to find failure points of materials. Non-destructive testing analyzed by deforming of materials. But this research is based on non-destructive testing method, which include crack detection through wireless power transmission based testing. What is non-destructive testing? Non-destructive testing is a collection of different inspection methods used singly in combined system to assess the quality and characteristics of materials and components without causing harm to it. In other words, we can say when we do destructive testing, we cannot utilize that material further any more. But in non-destructive testing, we can still employ it. Therefore, non-destructive testing is frequently utilized for identification, quantification, and size of both inherent and damage-related discontinuities. Through wireless power transmission, we use eddy current testing method to conductivity analysis to identify material heat damage detection and heat treatment monitoring have been developed using eddy current testing. Eddy current testing has gone different procedures, including single frequency method, multiple frequency method, swept frequency method, etc. So recently the ECT has started using flexible arrays for probe design. The various excitation issues are resolved with a high accuracy and wide bandwidth potential by the swept frequency techniques. We use wireless power transfer system which is traditional transmitter and receiver coil system, which is sensitive and to changing flux linkage and respond quickly to it. As an energizing circuit, two coils acting as a receiver and a transmitter, as well as burden make up a receiver and transmitter wireless power transmission system. So multiple components like capacitor and inductors, which in combined with the series and parallel make resonant circuits. The primary alternating magnetic field pyramids the highly conductive non-ferromagnetic material as an alternatingly powered coil of impedance reached it, produce continual and rotational eddy currents on our sheet. Where is non-destructive testing used? Non-destructive testing used in power generation plants, petrochemical industries, oil and gas refineries companies, marine industries use it. Aerospace bodies are aerospace bodies are inspected using non-destructive testing. Automotive and manufacturing companies also use it. Motivation of our project to detect the flaws or faults from metallic components normally used in different structures like aluminum and copper material which we have used in our project. Cracks initiated due to stress loading and its propagation through the structure lead to a fracture. Failure to its early detection in the structure like rail line, pipeline, and aeroplane results in a fatal accidents. To detect defect, wireless power transmission-based inductive coils will be investigated and designed. Problem statement. Destructive testing, especially in nuclear power plants, which is very hazardous, it can become the cause of heavy destruction in the existence of reactive nuclear material. So, wireless power transmission, non destructive testing would be a perfect solution for inspection of nuclear power plants. We cannot use the material after the examination in destructive testing, but we can reuse the things in a non destructive testing. This is the literature review which was taken from brandcarrot.com and cited here. It tells us about the eddy current production on our metallic sheets. However, it is unclear if he succeeded in sending power. The device in his patent are several materials are high and could conceivably send power quantities close to the megawatt range. Given the recent interest in a wireless power transfer, many research groups and companies are currently analyzing and developing power transfer systems that rely on resonant magnetic coupling. Several systems have been studied that use either resonator, sender, or receivers. This paper cited uh, from M.R. Marinda, Joe Fenty. The resonators in this experiment were identical coils and achieved 30% real power efficiency at 10 megahertz over a distance 7.5 times the radius of sending and receiving coils, which we also use in our wireless power transmission system to investigate our wireless power transmission efficiency. We use this paper. And this paper is taken from indeed.org. In metallic structure, it is essential to detect and quantify cracks for safeguarding healthy structure operational services like rail line, pipeline, aeroplane, and fatal results in a fatal accidents. Aims and objectives of our project. The main object is to design reliable and efficient probes for the detection of flaws on a surface of different materials. Our aim is to examine a component in a safe, reliable, and cost-effective manner without causing damage to the equipment, shutting down plant operation. That's why we want to design a non-destructive testing probes which help us without causing the damage to the equipment. This contrasts with the destructive testing, where the part being tested is damaged and destroyed during the inspection process. Methodology of our probe design. This circuit system implementation involves a circuit that is series connected to a component, where we have used two capacitor of 0.1 picofarad in a parallel to make it a half, and 1 ohm resistance and 10 microhenry inductance. We are using eddy current probes because it increases the scope of eddy current inspection by maximizing defective signals, minimizing noise amplitude, and discriminating between defect signals and noise. We have written some data of specification of our components, where we have designed our own inductance, which contain 15 number of turns and produce 10 microhenry inductance. Resistor of 1 ohm, capacitor of 0.5 picofarad, and they produce quality factor of 0.3 and resonant frequency of 71.2 megahertz. After that, sample of copper and aluminum sheets were used. We have done these cracks with the help of SRM20 Rowland's machine, which is present in Sakkara IBFA. Another sample of the copper metallic sheet is used and drawn some defects and cracks on this sheet with the help of lathe machines. We have written the dimensions over there, which contain different depth of cracks like 1.53, 1.63, 2.42, and 2 on a copper sheet, and 3 cracks on a 0.75, 1 and 1.5 on our aluminum sheet. We start our experimental procedure from these two coils, which these two probes. We have connected these two coils with the vector network analyzer machine through the port 1 and port 2. Where probe 1 and probe 2 are at 1 millimeter separation from each other and 2 millimeter takeoff from our metallic shields. The sample of aluminum was moved for 160 millimeter distance stepwise of 2 millimeter in terms for aluminum sheet, and it was moved for 300 millimeter distance stepwise of 3 millimeter gap for copper sheet. VNA was calibrated for sweep frequency from 50 MHz to 100 MHz with 3000 points division to analyze the S21 parameters. For numerical processing, the personal computer receives the VNA data signal and that was acquired for each scan point. This is simply experimental procedure diagram where we have designed, we have shown eddy current probes, base probes, and metallic sheet which were scanned by these probes, and our probes send data to the VNA machine where we get S21 parameters, and uh, the whole result is further uh, further divided into different algorithms, and we have analyzed different features from our personal computer using different algorithm on a MATLAB software. We have get these results from our VNA machine. So response from the vector network analyzer take the form of M shape and displays different responses depending on the geometry and liftoff. It includes S21 data with 3000 frequency point division for 140 millimeter scanning spots of an aluminum sheet at 2 millimeter interval. This main figure M type shape shows the output on a VNA machine, but the above figures which indicate that no crack 1, crack 2, crack 3, and crack 4, which generate different magnitude peaks, and they simply identify that our probes scan the sheet and analyze different depth of cracks. To detect these cracks, to analyze these cracks, we have used different algorithms of like base point features. This graph it depicts the magnitude characteristics of aluminum sheet, where dominancy and non-dominancy crack magnitude produce peak on the same graph. We have drawn three cracks on our aluminum sheet, which can simply be identified, and we have identified these cracks with a C1, C2, and C3. They generate a peak when our probes reach at a central position of cracks. After that, we use principal component analysis because evaluation of large data is challenging. We have taken almost 150 data, which is very challenging and time taking. So PCA techniques to condense large multi-dimensional data into manageable number of dimensions. Three prominent characteristics were chosen uh, and exhibited on a graphs where fracture positions were indicated. So PCA graph clearly shows the magnitude of crack 1, crack 2, and crack 3. After that, we have used independent component analysis and graph is plotted here. Fast ICA is also known as independent component analysis, which is a potential tool and identify the underlying methodology when other conventional method fails to meet. We have run ICA on this data to define the extract crack points from a large data. So the 1.5 millimeter deep crack C1 is the most prominent on the aluminum sample. Nearly 1701 samples were used to compute IC1, IC2, and IC3. This is the comparison of cracking points on all the plotted graphs, where we have shown magnitude, ICA, and PCA, all the three features and their cracking points. We have identified that when we were cracking on our aluminum sheet, we measured the distance of aluminum sheet, and this is the exact same distance on our results, which indicate which generate peak and indicate that it can be simply identified the crack 1, crack 2, and crack 3. These are the results of copper material. We have used copper sample, copper material also. Similar approach of non-destructive testing is also applied on copper material. Data is analyzed on several algorithms of PCI-CF. All the spotted were scanned using sweep frequency of 40 to 100 MHz with a 3 millimeter gap between each point. All plotted 5 cracks pointed, but few cracks have lower peaks due to their very low depth of cracks on a sheet, like 0.5 millimeter or 1 millimeter. So drag dotted red lines on each crack point indicate their exact point. Precise location of 27 millimeter, 96, 147, 219, and 261 millimeter scan location, which were also identified on our sheet and on these plotted graphs. So we have indicated with the C1, C2, C3, C4, and C5. Hence, in a conclusion, in this research, wireless power transfer based probes were designed for eddy current testing on materials. When evaluating material quantitatively without causing damage, these probes are highly useful instrument. For eddy current testing, wireless power transfer is a helpful and effective method. These probes based inductive, these wireless power transmission based inductive probes underwent non-destructive testing for identification of surface flaws, and several features were investigated experimentally. Utilizing magnitude ICA, PCA, and characteristics, quantitative non-destructive testing is employed on different materials and analyze their features. We have identified 3 primary fractures in aluminum material and 5 major cracks in copper were quantified based on their frequency characteristics. Hence, we have concluded that wireless power transmission non-destructive testing approach is more convenient, safer for non-defect detection. So we recommend for future that future research will focus on various techniques for detecting fractures on a variety of materials for the extraction of useful data. Using a VNA machine to evaluate fractures is costly. So our next study will focus on data extraction without a VNA machine, and it is worthwhile to investigate wireless power transmission based inductive resonance probes, as they are quite useful in evaluating complicated systems. And in final, by implementing such methodologies, our focus is to design wireless power transmission probes for testing concrete and non-metallic materials as well. These are some reference which we have studied using during our project. Thank you.